Hello, uh, this is the live session for Structure, Form and Architecture, the Synergy. It's an NPTEL course. The course instructor is Professor Shubhaji Sadhu Khan and I'm Shreya Shukla. I am a PhD scholar at IIT Roorkee and I am the course TA for this course. Today we will be doing week 7, assignment 7 of week 7. And I would like to clarify this that we only do previous year assignments here. We do not do this year's assignment. So I have 18 questions with me today. Some are more from the 22nd year 2022 questions and others are from previous years. So I will be discussing 18 questions for today. We will wait for 5-10 minutes for others to join and then we will continue the session. Hi, I don't know what your name is. Uh, It's Piku, I guess. Yeah, I am so sorry that the exam is this Sunday, but NPTEL gave us these dates. So that's how we are conducting the sessions. These dates were given to us by NPTEL. They started the session 2 weeks late, which was I guess on their end. So I'm really sorry, but it's not in my hand. It will be conducted on next Tuesday only. Because these dates, it was not in my hand to schedule all these days. It was NPTEL who gave us these dates and it was NPTEL who set the calendar. So basically, I think the discrepancy that has happened is that it started 2 weeks, the problem solving session started 2 weeks after the course was started. If it had started 1 week after the course had started, then it would not have been a problem. Okay, so it has been 5 minutes. We will start with the session. Meanwhile, other people who wish to join, they can join in meanwhile. We will not wait. So yeah, introduce again that today we are doing this live session for the course Structure, Form and Architecture, the Synergy. I am Shreya Shukla and I am the course TA for this course, and I would be doing assignment 7 for week 7 in today's session. And I would like to clarify that we do previous year questions in these live sessions. We do not do this year's questions. This is just for to help all the people who have enrolled to get a better grasp, to understand what kind of questions can come and usual trend of questions that form from each syllabus. So yeah, moving forward, I will not go in the definition today. So week 7 syllabus, again 5 lectures were covered in week 7, like every week. So this week's lectures that were covered were structure and architectural forms in windy areas, structure and architectural forms in seismic prone areas, structure and architectural forms in flood prone areas, cost effective structure in architecture, and structure and light in architecture. So just a second. Yeah, so in the first lecture, not the first, it's the, I think, the 31st lecture, structure and architectural forms in windy areas. So what all was covered under this presentation or this session was that introduction, what is wind in general, different kinds of wind, the prevailing winds, the seasonal winds and other things, then different types of storms, and then what damages do winds can do, catastrophic failures that can happen because of wind, and component failures that can happen because of the wind. And then we saw a lot of examples were given how strong winds can damage weak parts. For example, if there's a lightweight porch or a veranda, all those things can be disrupted by wind, high wind. And then it was discussed what is wind, what kind of wind load happens in a building, what kind of building shapes have effect on wind differently. For example, a circular shape would have less wind pressure compared to a square shape and other things. Then how wind affects the building spacing, how tall buildings are affected, and all other aspects of wind were covered. And then different kinds of structures were discussed, how wind resistant structural forms can be made. And then we learned that a dome shape, a pyramid shape, an egg shape, spiral wind shape, all these shapes are resistant to wind. So all these points were covered in this lecture. Then the next lecture, the structure and architectural forms in seismic prone areas. Again, it was discussed about what kind of earthquakes arise. The kind of different kinds of waves that happen in earthquake, P wave, S wave, and other things. The effects earthquake has on the earth, that there is a ground motion, there can landslides can happen, and then effects of earthquake on building, the kind of damage they can do, the kind of destruction they can do, and what are the main reasons of failure in seismic prone areas, because there are a lot of structural reasons also why earthquake damages are severe, and we can definitely avoid those kind of severe damages if we pick point on those structure points. And then design considerations about earthquake, which will depend on the size of the building, shape of the building, position of the building, and other things. A lot of these aspects were discussed, and a lot of these aspects were covered. And then different earthquake resistance techniques were discussed, like shear wall, like bracing, and horizontal bands, and other aspects were discussed. And then it was discussed what is bracing, different kinds of bracing, and all those points were covered. Then in the next lecture, structure and architectural forms in flood prone areas. Excuse me. Similarly, what is flood, how it what kind of load is exerts on the, and the damage that happens because of flood, and the damages that can happen because of flood, and the reasons for damage that happens, and other reasons, and different kinds of destruction, what all happens. And then how flood affects different kinds of building components. For example, how it affects the foundation, how it affects the walls, how it affects the roof. And then we had then it was covered that what kind of different kinds of what drive flood proofing, what wet flood proofing, all these kinds of techniques were discussed, how they levy, how these can help in design and tackling flood basically. Then cost effective structure and architecture, uh, what are the factors that affect the cost of construction, and how can we achieve cost effectiveness via construction techniques, via material use, and via different components. All these points were covered in this lecture. And then we saw some examples of cost effective structures and architecture. Then the last lecture was structure and light in architecture, and this lecture talked about um, how with the help of different kinds of structures we are allowing light to come inside architecture. And sorry, yeah, so how can we maximize light with the help of structural form, how can we modify light, and other points were covered. And it was also discussed different kinds of structures like space frames and trusses, how they help in adding light to the building, adding light to the structure, how they can be beneficial in adding light. And then different case studies from all around the world, different buildings were discussed, different case studies were discussed in this topic. So yeah, this is what was covered in week 7. Now we will proceed forward with our questions. I would again like to mention that these are all previous year questions, these are not this year question. So yeah, the first question for today. Any wind that has a perpendicular component to the line or direction of travel is referred as seasonal wind, prevailing wind, local wind, or crosswind. So to be able to understand this question, we would understand all 4 kinds of winds. All these 4 kinds of terms that are mentioned, we will understand what all these 4 terms mean, and then we will answer this question. So what is wind? Wind can be basically described as the movement of air from high pressure area to low pressure area. So for example, this is a low pressure area, this is a high pressure area. So the wind will go from high pressure to low pressure. So it is an air movement which has both direction and speed. Wind is an air movement, but it has a direction and it also has a speed. And it is made up of gusts and eddies and can be felt and not seen. Wind can be felt, but it cannot be seen. And other aspects of like wind, for example rain and snow, they can be felt also, but wind cannot be, they can be seen also. Wind cannot be seen, it can only be felt. So this is what wind is. So what is prevailing wind? Prevailing wind is first of all also called permanent wind. And prevailing wind are winds that blow from a single direction over a specific area of the earth. And areas where prevailing winds meet are called convergence zones. And generally these prevailing winds, they blow east to west rather than north to south because of the orientation of earth and other reasons. So they are called prevailing wind or permanent wind because they only specifically go in one direction for a specific large amount of time of the year of the and specific region also. That's why they are called permanent winds. Seasonal winds, the winds that change their direction with onset of different seasons. So that's why they're called seasonal winds, because with different seasons they change their direction, while a prevailing wind, they never change their direction. So these are called seasonal winds, and seasonal winds are movements of air repetitively and predictably driven by changes in large scalar weather patterns. Seasonal winds occur in many locations throughout the world, and the most common and very well known example is monsoon. So monsoon is actually a seasonal wind. It is not just the onset of rain or how we think it is. It's actually a seasonal wind. Monsoon is a seasonal wind, and it occurs in low latitude climates that seasonally changes direction between winter and summer. And monsoon is very prevalent in India, as we are all very familiar with that fact. Then local wind. Local winds occur due to the movement of air between high and low pressure systems within small areas. They are called local winds because they are regional, not regional also, even to a smaller scale than a region. In a very small part, these winds happen because of different kinds of climatic conditions that are happening for various reasons. For example, there might be a lake present or a water body present, and that may affect the wind pattern locally. So that would be local wind. And as there are different types of winds, each one is slightly different from the other. Local winds always have a significant effect on climate in a particular region, and these blow only during a particular period of the day or year in a small area. And the example of local wind could be land and sea breeze. Then crosswind. So, like prevailing wind and seasonal wind and local wind, they are different kinds of wind that are usually, when you ask about what are different kinds of winds, these are the three different kinds of winds that are talked about, mainly based on how longer they are staying, where they are happening, and how they are happening, and if they're changing direction or anything like that. So they are categorized on that basis. So now what crosswind basically is, it's a wind that has a particular perpendicular component to the line of direction of travel, and it affects the aerodynamics of many forms of transport. For example, this is an object that is moving in this direction, and then wind is going on a slightly different direction. So that wind will have two components. One component, if we convert it into vector, one component would be in the direction of the transport, and the other component would be parallel to it, perpendicular to it. So that's why this is crosswind. It's a very technical term rather than defining what kind of wind it is based on direction and time and other reasons. It's a different term which is based more or less used when we are talking actually about transport or an object and how wind is affecting that thing. That's when this term is used, and it affects the aerodynamics of many forms of transport, of course. And moving non-parallel to the wind's direction creates a crosswind component on the object, and thus increasing the apparent wind on the object. So if a wind is in this direction, and I am moving in a very not in this direction, but rather on an angular direction or any other direction, so there would be a higher force of wind on my object, because of course there is also a perpendicular force that will be acting on it if we change it into vector form. And so in some cases, this crosswind has been used for advantage. For example, sailing. In sailing, the crosswind is used as an advantage, and the sailing in a boat which has a sail, it will go in that direction, or it can help you change directions. And also on the other side, it may also it moves the path of vehicles, and it can also be a hazard in some cases. So our question again was that any wind that has a perpendicular component to the line or direction of travel is referred as. So as we have understood all these four terms, we know the answer would be crosswind, because it has a perpendicular component to the line of direction. Basically what it means is that, for example, this is my object, and this is the direction of wind. So wind is actually acting on my object in a particular angle, and when you do the vector components of this particular angle element, you will find that one thing would be going in the direction of the transport, and the other would be perpendicular to it. So because it's acting at an angle, and it can be divided into two different vector components, that's why it has a perpendicular component and it has a parallel component. So the answer would be crosswind. Arrange the following building shapes responsible for creating high to low pressure of wind. So three different shapes are given here. A is a circle with a pointed edge, B is a mixture of different kinds of squares and rectangles, and C is a rectangle with curved edges. And now the question is asking, you have to arrange them from high to low pressure of wind happening on this. So we have to figure out which of these shapes will have highest pressure of wind happening around it, and which will have the lowest happening around it. So coming with this figure, so we have three different shapes here. We have a circle, we have a square, and we have a dynamic asymmetric structure combined with different squares and rectangles. Now, when and then we have these patterns of winds which are going, and it is shown how these patterns of winds are acting with the surfaces. For example, in the circular shape, the wind just has a very swift movement, and it just goes around the building and then goes back into the direction. While in the square, the 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 layers or the patterns or the waves of wind that are acting directly on the face of this square. The square is not just a square, it will be a 3D base. So when it is acting on the, it's attaching on the face, then it is forming some eddies, these circular motions in which the wind twirls. It's called an eddy. Eddy currents are being formed here, and also eddy currents are being formed on the back side of the building. And then we see this building with different kinds of surfaces, and then the third kind of building, it has too many different kinds of surfaces. It does not have four surfaces, it has too many different surfaces. And then you see that when wind is coming here and coming to the different surfaces, so too many eddy currents are also happening, because you are also getting too many surfaces. For example, imagine this is like an elevation. So one surface is here, one surface is here, and the other surface is more behind. So wind will come, and when it comes in effect in front of these all faces, then it forms different eddies in different points. So because of the formation of these eddy currents, more pressure is happening. And as you can understand from this figure very clearly, that because of the availability of of too many surfaces, the last figure has more eddy currents forming, and the last figure has more pressure happening on him. While compared to the circular form, you see that there are no eddy currents forming as such. So going back to the question again, so we have to figure out, we have to answer it from high to low pressure wind. So we have to first pick which will have the highest pressure of wind happening. So as we can understand, yeah, so as we can understand, the B figure, because it has different surfaces on it. Although one mistake that I find in this question is that they should have also mentioned the direction of wind in this, because that will also change a lot of things, I feel. So nevertheless, the direction of wind has not been mentioned in this question. So we'll just go by the shapes. So the B figure has a lot of different edges. You can see it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different edges. The C has 4 different edges, and A is just one single circumference. So B has a lot of different edges, and we know, like from what we have just learned, that a lot of eddy currents would be forming if wind would come in any direction on B. So B would have the highest pressure. So our answer would start from B. Now we have to see which. Next we go, and when we see the figure C, although it's not a complete rectangle, it has some curved edges, but because it still has four faces, and it still has different faces, and it still has a rigid fixed one surface, then it will also have some eddies form at the edge of that surface. Although when you compare that figure C with the proper rectangle, you will see that the proper rectangle will have more higher pressure, because more eddies will be formed compared to this C shape, because this C shape actually has a little curved edges which will help the wind to go by swiftly. And then when we come to the figure A, it's a circle and it has an extended edge. So when you will compare this figure A with the proper circle, then you will see that this A will actually have more pressure, because still it has one edged thing, one flat thing where wind can come and strike on, rather than a circle where the wind just flows around it. So yeah, compared to a circle, this A will have more higher pressure, and compared to a rectangle, this figure C will have lower pressure. but we have three shapes to deal with and we have to mark it from high to low. So our answer would be B, C and A, and it answer would be B, C and A, B. Excuse me. Yeah. Moving forward, third question. Dash refers to one level of a building that is significantly more flexible or weak in lateral load resistance than the stories above it. So we have four options: soft story, clear story, multi-story and hard story. And the question is asking that which one of the following does it, what refers to one level of a building that is significantly more flexible or weak in lateral load resistance. So the question is asking that okay, we'll go forward with all these four terms and then we will answer this question. That would be easier. Soft story. So what is a soft story? I'll just zoom in these figures a little. Yeah. So, soft story refers to one level of a building that is significantly more flexible or weak in a lateral load resistance than the stories above it, and the floors or the foundation below it 70% or greater reduction from one floor to the next according to the modern International Building Code (IBC) definition. So what happens in soft story is that, for example, you have 2 3 stories and your ground story, the one which is on the ground, it may be a little weak compared to the stories above. It could be weak because of a lot of reasons. For example, usually in buildings which have stilt parking and there is no wall component and other things, it tends to be a little more weaker compared to the other stories. So the floors or the foundations or these wall columns, whatever is in these soft story, which is not as strong or as rigid as the above stories, it can damage when you have an earthquake or other kind of disaster, because it cannot take as much load as the above stories are taking. So if you look at this figure, you can see that uh, building A has all the stories which are very rigid, and none of those stories are soft stories. So when earthquake happens, the building will just sway a little and then come back to its place. But in the case B, if there is a soft story involved, for example, the ground floor has a soft story and the above floors are rigid, so when an earthquake happens, the soft story would move and the above building would just stay in its place, but the soft story is moving and that will create a load and pressure, and there would also be a lot of stress which would be happening on the joints of this soft story with the above stories, and in worst cases there can happen a collapse if it's too weak. So that is what a soft story is. Then clear story. In architecture, a clear story, clear story, or clear story, or overstory is a high section of wall that contains windows above eye level. Its purpose is to admit light, fresh air, or both. So usually it has this term, this clear story term has been used to in describing an element of older buildings, but now it is used in a lot of forms. So what it is that there is a high wall, and that high wall has windows which are above your eye level. You cannot see what is happening in that thing because it's above the eye level, and the purpose of these high windows that were created on these high walls was to admit light, and that's why it is called clear story. So in the figure that is right next to the soft story figure, the part which is highlighted in gray is the clear story. If you see it as an elevation, there is a ground and then the windows which are on the floor above or way above your eye level, it is that whole thing is called the wall is called clear story. Then multi-story. Multi-story is a term that is used for buildings to identify a kind of building which has a lot of different stories. For example, story is a floor in architecture language or in construction language. So if there's one floor, then it is just a single floor. It has two floors, then it's a double floor building. But if it has a lot of several floors and it is not easily countable, you can just easily mention that it's a multi-story building. So this is what multi-story means. And I searched for this term hard story, but I didn't find any of the definition or any of the relevance of hard story in architecture or construction anywhere. So I have not added any kind of definition because there was no such term that exists in architecture. So coming back to our question, dash refers to one level of a building that is significantly more flexible or weak in lateral loads resistance than the stories above it. So from what we have just learned about all these terms, we know the answer would be soft story. Moving forward, question number 4. Richter scale is used to measure the dash intensity, tsunami, earthquake, flood, or wind pressure. So there are a lot of devices that are used to measure earthquakes, the wind pressure, and water levels and whatnot. There are several devices, and of course, I'm not an expert in all those things, but we all know a few things which are in common knowledge. And there are a lot of technological developments, so there are many devices, many things that have been invented to measure these kinds of the intensity of these kinds of hazards or disaster. So our question is that what is Richter scale used to measure? So yeah, I've just defined a little what a Richter scale is. So Richter scale, also called the Richter magnitude scale, Richter's magnitude scale, and the Gutenberg Richter scale, it is a measure of the strength of earthquakes. It was developed by Charles Francis Richter, and hence it is called a Richter scale, which was named after him. And in his landmark paper in 1935, he called it the magnitude scale. And this was later revised and renamed the local magnitude scale, and it was denoted as ML. So it is a formula based on the amplitude of the largest wave recorded on a specific type of seismometer. A seismometer is a meter which measures the seismicity and the distance between the earthquake and the seismometer. So this Richter scale, not scale, this Richter scale actually works on a formula which is based on the amplitude of the largest wave that was recorded and the distance between the earthquake and the seismometer. So there would be a seismometer which is recording the amplitude of waves that are coming. So the largest recorded amplitude and the distance of the seismometer from the earthquake epicenter. And there's a formula which uses these both numbers, and then we convert it into a scale. And that scale was specific to California earthquakes and crust. Other scales based on wave amplitudes and total earthquake duration were developed for use in other situations, and they were designed to be consistent with Richter scale. So Richter scale, as it was devised in 1935, and of course all these scales they must have developed with time, and this specific scale, the Richter scale, was designed specific to Californian earthquakes, and hence more work was done on this scale. And moving forward, there are a lot of new scales now which measure different kinds of, which includes more parameters, for example, like total earthquake duration and other things, to give a scalar quantity, to give us what is the magnitude of an earthquake. So yeah, this is just this is Charles Francis Richter, a picture of Charles Francis Richter working with a seismometer, and then we have a diagram which basically shows how Richter magnitude is happening and how Richter scale is happening. And also a seismograph is a graph which records the magnitude of the earthquake that is happening. So that is recorded, and then all those things are calculated, and then they're placed. And if you can see in the Richter scale, or the that has been given here, Some of the most famous earthquakes have been mentioned and where they lie: the Alaska earthquake, the San Francisco earthquake, the California earthquake, the Salt Lake City earthquake, and others. So, yeah, the Richter scale is used to measure the earthquake intensity. Question number 5. Which of the following brick bonds has cavity in it? Flemish bond, zigzag garden bond, English bond, and rat trap bond. We will see what all these 4 bonds are and then we will answer this question. So, moving forward, Flemish bond. Flemish bond or Flemish bonds, it's a masonry, and in bricklaying it's an arrangement of bricks such that each course consists of alternate bricks having short sides and long sides. Short sides are called headers, long sides are called stretchers, facing outward with alternate cores being offset. A Flemish bond pattern consists of each course of alternate headers and stretchers. The patterns arrange such that every header is centrally supported over the stretcher below it, and the facing and backing of the wall have the same appearance. So what happens in Flemish bond is are alternate headers and stretchers that are kept. So there would be one stretcher, then one header, one stretcher, one header, one stretcher. This alternate band is made in one layer and then the same thing is repeated. So it's the same layer above one each other, but to avoid joints coinciding, which will actually have no structural integrity in the wall, we shift them a little with the help of uh, uh, half of a half of a header, which is called a coin. So we use that kind of brick and then we shift it. So what happens is that this header in the second layer would be right in the middle of the stretcher of the first layer. So as you can see from the image, that is what happens in Flemish bond. One one header, one stretcher, one header, one stretcher, and then all the courses have this similar layer. And in Flemish bond, the first layer and the third layer look identical, while the second layer and the fourth layer look identical. So that's how it is made. Now move, and if you can see in the image, when the first course is laid, and then the blue mark, if you can see what is highlighted in blue here, is actually what I was mentioning, the coin, QUOIN it is called, and then it is placed to slightly shift the second course so that it doesn't, all the joints don't coincide on the joints, otherwise there would be no stability. And this is how it is made. So it's a 200 mm thick wall. If you can see, it's 2 brick size wall, and that's how the first course is laid and then the second course is laid. Then what we see in elevation here is what is the figure on the left: alternate bands of headers and footers, not headers and footers, headers and stretchers. Now coming to English bond, it is also kind of masonry, and it consists of courses of stretchers, sides of bricks, alternating with courses of headers, end of bricks, throughout a wall surface. So how is English bond different from Flemish bond? Is that in Flemish bond, in the same layer you have stretcher and header laid one after each other consecutively. But in English bond, one layer is all stretchers, one layer is all headers, then again the layer is all stretchers, then again the layer is all headers. So that's how English bond is constructed. So it can be constructed for almost all wall thicknesses. This bond is strongest among all other bonds. No continuous vertical joints are formed. In the elevation, the alternate course either shows headers or stretchers. Every header is an alternative course, comes centrally over the joint formed by 2 stretchers below it. And this is how the first course is laid. If you can see the figure on the right, that all the stretchers are being laid directly, and then above it all the headers are being laid, and then again above it all the stretchers will be laid. So this is how English bond is formed. So I have added both the images, the plan and the elevation, to help you make understand these bonds better. Then zigzag bond. So zigzag bond is a bond in which the bricks are laid in a zigzag pattern throughout the joint. Uh, Hello, somebody has asked a question that if I were going to provide the notes of the chapters. I have so far, my job as the course TA is to take the live sessions and to prepare these PPTs where I solve all these previous year questions. And if you would check your mail and or you check the portal, NPTEL portal, you would have had a link where all these PPTs are uploaded, so you can access those PPTs from there. So I only have this PPT, I don't have any other extra notes. And you can study, of course, from the NPTEL lectures themselves, or you can refer the previous year questions from these PPTs that I have made. They're all they are. You must have a mail link, or if you go to the NPTEL website or the Swayam website, you will see there would be a portion where you will see the live session recordings or something like that. It gives you a access to a Google Drive link which has all these things, so you can check there. But this is all the scope that I have. I do not have any other notes. Yeah, so zigzag bond is a bond in which the bricks are laid in a zigzag pattern throughout the joint. The herringbone and zigzag bonds are the example of the same type of bond. It is used for paving works in residential constructions such as floors, footpaths, because of its attractive appearance. So zigzag bond is not actually used in wall construction. It is either used in paving work or flooring work. And this is how zigzag bond looks like in plan. So it's just a zigzag. Oh, I've added a long image. This is not a zigzag bond. This is the diagonal bond. I have added the wrong image. I'm so sorry. So as you can see in this image, this is how the zigzag bond looks like. It would be like a zigzag pattern, a chevron pattern. You would see different V's happening. So this is how a zigzag bond looks like. Then rat trap bond. Rat trap bond is a modular type of masonry bond in which the bricks are placed in a vertical position, which creates a cavity in the wall while maintaining the same wall thickness as that of the conventional brick masonry wall. So the look of rat trap bond, if you go by the elevation, it looks exactly like Flemish bond, but it is different from Flemish bond how it is being arranged. So in Flemish bond, for example, you are arranging one header in front and then you arrange two stretchers to cover the length of that one header. But what you do in this rat trap bond is that there happens to be a cavity. Basically, for this specifically in the rat trap bond, the length of this brick is a little higher compared to the width of this brick. So it is laid vertically in the sense that if you see if you see here that a brick has three dimensions, right? This rectangle, uh, three dimensions. There would be a thickness, there would be a height, and there would be a width. So there would be, so in this case we are making it stand vertically, which makes this thickness, the front thickness, comparatively less, and this helps in creating a cavity in between. So in the same in the wall while maintaining the same thickness as that of the conventional brick masonry bond. It is also known as a Chinese brick bond. The purpose of using this type of masonry bond is to reduce the number of bricks and mortar required as compared to the English or Flemish bond because of the cavity formed in the wall. And in India, rat trap bond was brought by Laurie Baker, and he introduced it in Kerala in the 1970s. and he has used it extensively because of its lower cost construction, the reduced material requirement, and better thermal efficiency, because cavities are being created in this kind of brick layout. So it has better thermal efficiency also as compared to a conventional masonry wall, and it does not compromise the strength of the wall also. So going back to our question, it was which of the following brick bonds has cavity in it? So as from what we have learned just now, that it's rat trap bond. Rat trap bond is the only bond amongst all these three that has a cavity in between. So this is how the rat trap bond is being laid. So this is what I was trying to explain, that it, as when we say that we place the brick vertically, we basically mean that it is being placed instead of, for example, this is your header, this is your stretcher, this is a normal bond, but in Flemish bond you place this brick like this, which makes this width a little less, and hence it helps in creating a cavity in the brick layout. So this is how it looks like. I have added a plan and a real photo also for you to understand. So the answer is rat trap bond. Now question number 6. Dash is a low wall built at the side of a river to prevent it from flooding. So we have 4 options: crown, levee, mount and peak. And the question is asking, dash is a low wall built at the side of a river to prevent it from flooding. So I searched these terms: crown, mount, peak and levee. All these terms I searched if they mean anything in architecture or construction, if they mean anything with relation to flooding. So crown, mountain and peak, all these terms do not mean anything in relation to flooding. So it's apparent the answer would be levee, but we would just go through what is a levee so that we understand the concept of a levee, and if there is any other kind of question that is based on levee. I'm not sure if it's called levee or levee. It's probably levee. So you can answer that. So we will cover a little about the levee. A levee, dike, embankment, flood bank. So a levee is also called a dike, embankment, a flood bank, stop bank. It has many terms. It is a structure that is usually earthen and that often runs parallel to the course of a river in its floodplain or along the low-lying coastlines. The purpose of a levee is to keep the course of rivers from changing and to protect against flooding of the area adjoining the river or coast. Levees can be naturally occurring ridge structures that form next to a bank of a river or be an artificially constructed fill or wall. So levee can be of 2 types. They can naturally emerge also, they can be natural, and they can be man-made. So what is being done basically is that along the bank of a river, along the edge of a river, we construct a structure so that when the river flow increases or the river water increases, it does not flood to the land right next to. This is what a levee does. And there is also a contradictory thing about levee, that they can be bad for the environment and other reasons, and we are not going to go in that right now. And also this is not a new technique or a new term. It has been used in the ancient civilizations like the Indus Valley, Egypt, Mesopotamia and China. These civilizations, they built levees. So it's an ancient knowledge, it's not a new system. So if you can see in this image, for example, the first part shows how the river bed looks like before construction. So there is a river bed that is going, and there is a plain on both sides of the river. So when this river is getting more flow of water, you can see how the plain right next to it, how the land right next to it is getting flooded. So after image, when you see the image below it, the after image, it shows that when you built a levee, it's a man-made structure here. We can see it in the form of a trapezium. So we built a man-made structure and we restricted the width of the river with this structure. So even if the water flow increased or the water level increased, it is not able to flood the area because there is this structure in between now. So the river stays here and we prevent flooding. So this is how a levee works. just showing two examples of levee that I found very interesting. The first image, if you see, this is a house in the middle, and it is, the level of this house is way below the level of the water that is near it, but the whole surrounding of this house has levee around it, because of which the water is not flooding this area or uh, going inside that area because of this levee. And then in this second example, you can see a riverbed, and then you can see a continuous construction line, that is construction that is going, and it's a levee which is actually protecting the city from this riverbed in case the river flow increases. So yeah, our answer is levee, and we have also understood what a levee is for future questions or future references. Which of the following is not a seismic wave? S wave, love wave, sigma wave, or relay wave? Rayleigh, not relay, Rayleigh. S wave. S waves are also called as secondary waves, shear waves, shaking waves, and they are transfer waves that travel slower than P waves. Uh, in this case, particle motion is perpendicular to the direction of wave propagation. And imagine a slinky partially stretched, except this time lift a section and then release it. A transfer wave will travel along the length of this slink. So this is what S-lay wave looks like in the image on the right. So a slinky is basically a spring kind of thing. So they are saying that to understand an S wave, what you do is you partially stretch that spring kind of thing and lift a section little and then release it, and then you will see that the wave that forms is like this. So that is an S wave. Love wave. In seismology is basically the study of earthquakes or other relative seismic activities. Love waves are surface seismic waves. For better understanding, there are actually two types of waves in seismology, which are body waves and surface waves. So S waves and P waves are actually body waves, and love waves and Rayleigh waves are surface waves. So they cause horizontal shifting of the earth during an earthquake. Augustus Howard Hugh Love predicted the existence of love waves mathematically in 1911. That's why they're called love waves. It is named after Augustus Edward Hugh Love. They form a distinct class different from other types of seismic waves such as P wave and S wave, both body waves, or Rayleigh waves, another type of surface wave. Love waves travel with a slower velocity than P or S waves but faster than Rayleigh waves. These waves are observed only when there is a low velocity layer overlaying a high velocity layer or sublayers. So what happens in love wave is that a horizontal shifting of earth happens during an earthquake in love because of love waves. So S wave is just a wave that goes by, but in love wave, horizontal shifting of the earth is also happening. Then Rayleigh wave. A Rayleigh wave rolls along the ground with a more complex motion than love waves. All, although Rayleigh waves appear to roll like waves on an ocean, the particle motion is opposite of ocean waves. Because it rolls, it moves the ground up and down and forward and backward in the direction that a wave is moving. And also what happens in Rayleigh wave is basically it looks like a ripple. So not only it goes up and down, it is basically this up and down motion is like a rolling motion. So that's why it's called a roll wave also, or a Rayleigh wave. And I searched this term sigma wave with respect to sigma wave. So sigma wave is actually a very a term which is used in physics or mathematics, and I'm also not very much uh, at par with all these physics and mathematical terms anymore, because after 12th I have not also studied all these things. So sigma wave, I actually had no clear definition that I could define here or explain here or be able to understand also from my point of view. So I have not included that here. And clearly our answer is C, sigma wave, because all other three are seismic waves. But sigma wave is a representation in mathematics or physics. It's not a seismic wave. So yeah, this is what I was talking about, the different kinds of waves. So we have two kinds of waves: surface waves and body waves. Surface waves are love wave and Rayleigh wave, and body waves are P wave and S wave. Which of the following is not a seismic wave? So the answer is sigma wave. Moving to question number 8. The glass used in the City of Arts and Sciences in Valencia is mainly for filtering daylight, obstructing daylight, minimizing daylight, or absorbing daylight. So we will see first how the City of Arts and Sciences in Valencia looks like, and then we will answer this question, because on the basis of how it looks like, we can very easily answer this question. So this is why I keep repeating this to everyone, that before your exam you have to be aware of the most famous buildings and how they look like, at least to be able to answer these questions. Because if you do not have an image in your mind, because most of the times you won't be provided an image. In some questions you would be provided an image, but not always. So you have to be able to remember what a building looks like, what are its important features, so that you can remember actually how it looks like, and then you can very easily answer most of the questions. So this is how two of the buildings of this entire City of Art and Sciences looks like. So it's actually a cultural and architectural complex, and it is located in Valencia, Spain, and it is the most important modern tourist destination in the city of Valencia and one of the 12 treasures of Spain. So I had the privilege of actually visiting the all these this whole complex in October last year. So because I have actually visited this thing, I actually can very easily remember what all those buildings look like. But if you want to be able to answer these questions, you have to remember how these buildings look like. So you have to search the names, you have to learn a little facts about it, and then you will actually clearly remember them. So this complex has 7 buildings, and 6 of these buildings are designed by Santiago Calatrava, who is a very famous Spanish architect and structural engineer, I'll say. And he creates very modernistic, very scientific buildings, very different looking buildings, and derived from various different shapes or ideas. So Santiago Calatrava he's very famous, and he has a lot of work done in Spain, and he's a very famous Spanish architect. So in this complex there are 7 buildings, and 6 of those buildings are designed by Santiago Calatrava, and one building, La Oceanographic, which has this building, because we have talked about La Oceanographic in a lot of previous assignments and in a lot of previous lectures. That's why you might remember La Oceanographic. That one building is designed by Phoenix Candela, and it uses a curvy flower like shell structure, if you remember how it looks like. And the other 6 buildings are designed by Santiago Calatrava. So I won't say the name of all the 7 buildings, because there is no point remembering or what are the names here, but you must remember how they actually look like. And this is a panoramic view of the it's actually a 1.2, yeah, or 1.5 kilometer stretch, and all the 7 buildings are located in this 1.2 1.5 kilometer stretch, and you can visit all these buildings together. There is a museum, there is an underwater oceanarium, and there's a science museum, there is an art center, all these different kinds of buildings. And this is a panoramic view to be able to give you an idea how all these buildings look like. uh, the filtered sunlight is direct sunlight that fills the room most of the day, but it is filtered. It is called filtered light because it is filtered by curtains, blinds, maybe a tainted glass, maybe even trees. So it's direct sunlight that is filling a room, a filtered sunlight, but it is filtered with some or the other kind of object. For example, a curtain or a blind or a tree or a tainted glass or any kind of glass, which is like not exact complete impact on the uh, persons inside the building, but it is direct sunlight. And these are some of the pictures from the inside of two of the buildings in this complex. As you can see, because of how the structure is being used here, or how the structure is in being used in combination with glass and other objects, and not objects, other materials like different kinds of PVC sheets or other things, you can see how well the daylight is coming in, how different shadows and patterns are coming in. So it's very evident here. So, and again, two more images to show you how different kinds of shadows are, play of light and shadow in the interior of the buildings that have been designed in this complex. So our question was that the glass used in the City of Arts and Sciences in Valencia is mainly for. So they're not for absorbing daylight, and as you can see how open these indoor areas look like and clear, then it is definitely for not for minimizing daylight, because we are actually allowing a lot of daylight. It is also not obstructing daylight, as you can see from the images very clearly that a lot of sunlight is coming in. So it's clear from our options and from these images that we have seen and from what we have understood this structure looks like, that the answer would be filtering daylight. Yeah. So yeah, of course, glass can be used in a lot of ways. It can be used to obstruct daylight. It can be used to minimize daylight. It can be used to absorb daylight, of course, depending on the use. But if you remember, if you can see these images, you can see how none of those options are fitting here because a lot of daylight is coming in. So we're not obstructing it, and you can see clearly how open the image on the right is. So you can see how directly the sunlight is also coming. So we're not even restricting it, and of course we don't have a problem of observing the daylight because it's all coming in. So yeah, we're just trying to filter it with the help of different structures that we have, so that we have an interplay of shadow and light in the inside the buildings. So the answer would be filtering daylight. Moving to question number 9. Which of the following structural bracing system is shown in the image below? So an image is being given here, it has been given here, and then it's being asked that what kind of structural bracing system is this? Diagonal, K, chevron or V? So we will just quickly see what all these bracing systems are. So diagonal bracing. Diagonal bracing is a structural component of just about any building. It provides lateral stability, preventing the collapse of walls, decks, roofs and many other structural elements. So basically this bracing, what we say is, bracing is done just to provide more support to to a structural system, so that you can make it more stable, more stiff. And bracing is, I think, usually used in, if I'm not wrong, it's used in wind and earthquake situations. So yeah, in K braces connect. So all these bracing, they are named after how they look like and the pattern in which they are being attached. So diagonal bracing, if you see the image on the left corner, the first image is single diagonal bracing, second image is double diagonal bracing. So you can see diagonal bracing is basically one edge connecting the one edge to the other edge. It's a diagonal thing that is happening from one edge to the other edge. So that's a diagonal bracing. Then we have K bracing. So K braces connect to the column at mid height, and this frame has more flexibility for the provision of openings in the facades and results in the least bending in floor beams. K bracing is generally discouraged in seismic regions because of the potential for column failure if the compression brace buckles. So what happens in K bracing is that is this if this is one floor, then from the middle of this floor you will have two braces coming out, and all those braces would also be attaching to the middle of the floor. So in the sense that it looks like a K. If you see the image on the right hand corner, that is a K bracing. It is called a K bracing because it looks like a K. Then chevron bracing. Chevron braced steel frame, also known as chevron based steel frame or chevron bracing, is also known as inverted V braced frame or IVBF. It is concentrically braced frame configuration commonly used in practice. Primarily resisting the lateral loads with truss action, the IVBF provides very high lateral elastic stiffness and strength. So chevron bracing basically looks like an inverted V. And V bracing, as the name suggests, it will look like a V. So what happens in chevron bracing is that edge of column and edge where the column and floor are being joined, the brace goes to the mid center of the floor above and then down. And in V what happens, the upper edge goes to the down of the floor and then up. So that's how V and chevron look like. So two diagonal members forming a V shape extended downwards from the top two corners to a horizontal member and meet at the center point on the lower horizontal member. Inverted V bracing, also known as chevron bracing, involves the two members meeting at center point on the upper horizontal member. And if you can see from these images clearly what it looks like. So we will go back to our image and you can see that this is not a diagonal bracing because it is not connecting the edges. It is not a K bracing because the center of the column, the braces are not emerging from the center of the column. So this is either chevron or V because of the pattern, and as you can see it's an inverted V. So our answer would be chevron bracing. Also I would just in case just for people to remember this thing by, because chevron may be a new word or a confusing word. So this pattern is actually called chevron pattern, the whole zigzag pattern. So like we saw in the zigzag uh, bond which is used in floors, this is exactly how it looks like. So this pattern is called chevron pattern. So you can remember maybe this with the help of this, that this pattern, this zigzag pattern is called chevron pattern, and maybe you will remember this kind of question with the help of that. Question number 10. The following illustration is an example of strike slip fault, normal fault, reverse fault or longitudinal fault. So what is a fault? First of all, a fault is a fracture or zone of fractures between two blocks of rock. Faults allow the blocks to move relative to each other, and this movement may occur rapidly in the form of an earthquake or may occur slowly in the form of creep. Faults may range in length from a few millimeters to thousands of kilometers. And then coming to strike slip faults. They are vertical fractures where the blocks have mostly moved horizontally. The cause of strike slip fault earthquakes is due to the movement of the two plates against one another and the release of built up strain. As the larger plates are pushed or pulled in different directions, they build up strain against the adjacent plane until it finally fails. So what happens in strike slip fault is that first of all it's a vertical fault. So there are two pieces of land and it's a vertical fault. It's not inclined, it's vertically located. And what happens in strike slip fault is that this fault and then these two land, they move horizontally. Normal fault, a dip slip fault. It's also called a dip slip fault, in which the block above the fault moved downward relative to the block below. This type of faulting occurs in response to the extension. In a normal fault, the block above the fault moves down relative to the block below the fault. This motion is caused by extensional forces. Yeah, the whole same thing is getting repeated, I'm sorry. Yeah. This fault motion is caused by extensional forces and results in extension. Other names of this fault are normal slip fault, tensional fault, or gravity fault. So what happens in normal fault is that first of all, it's a diagonal kind of looking fault. It's not a vertical fault like in strike slip faults. And yeah, so in this what happens is that the block above the fault moves downward and the block below the fault moves upward. So it's like this kind of direction that is happening, up and down, and they're moving away from it. Now, reverse fault. It is opposite of normal fault. A reverse fault forms when the rocks on the uphill side of an inclined fault plane rise above the rocks on the other side. Reverse faults often form along convergent plate boundaries. In a reverse fault, the block above the fault moves up relative to the block below the fault. And this fault motion is caused by compressional forces and results in shortening. A reverse fault is called a thrust fault also if the dip of the fault plane is small. And then what is a longitudinal fault? It's any geological fault with its strike parallel to that of the regional structure, and a fault whose strike is parallel with that of the general structural trend of the region. So coming back to this figure, you can see that first of all this figure shows that it's a vertical fault because it's not inclined, the fault, it's vertical. Second, you can see one arrow which is showing that the land is drifting like this. So our answer would be strike slip fault. Moving to question number 11. Which of the following is not a type of storm? Tornado, hurricane, derecho, or tsunami? So what is a storm? A storm in generic terms is used to describe as a large variety of atmospheric disturbances. It can range from ordinary rain showers and snowstorms to thunderstorms, uh, wind and wind related disturbances such as tornadoes, tropical cyclones, and sandstorms. In meteorological terms, a storm is restricted to a cyclone with a strong low pressure center, strong winds which can range from 103 to 117 km per hour, accompanied by a heavy precipitation, at times lightning and thunder. What is a tornado? A tornado is a violently rotating column of air. A tornado keeps rotating, and it's very violent, and it's like a rotating column of air extending from the base of a thunderstorm down to the ground. So it comes from the thunderstorm and comes down to the ground. Tornadoes are capable of completely destroying well-made structures, uprooting trees, and hurling objects through the air like deadly missiles. Tornadoes can occur at any time of the day or night and at any time of the year, and this is how a tornado looks like. And I think we call it bavander in Hindi, if I'm not wrong. Hurricane. Hurricanes, known as tropical cyclones, are low pressure systems with organized thunderstorm activity. They gain their energy from warm ocean waters, and as storm systems strengthen into hurricanes, the surface winds move continuously in circular motion. So what happens in hurricane is, first of all, uh, uh, they emerge on the surface of warm ocean waters, and then because of the when this whole storm system is coming into play, the surface winds start moving continuously in circular motions. The direction of circulation is different depending on where the storm is located. It is counterclockwise in the northern hemisphere and it is clockwise in the southern hemisphere. And this is how, if you see the first image on the right top corner, that is how a hurricane looks like. Then derecho. A derecho is a widespread, long-lived, straight-line windstorm that is associated with a fast-moving group of severe thunderstorms known as mesoscale convective system. Derechos can cause hurricane and tornado force winds, heavy rains, and flash floods. So derechos can actually cause hurricane and as well as tornadoes, and they're basically straight line looking like a windstorm. And you can see in the image how the entire how the entire storm looks like a long line that is going on. Then tsunamis. So tsunamis are waves. Tsunami is nothing but a kind of wave. Tsunamis are giant waves which are caused by earthquakes or volcanic eruptions under the sea. Out in the depths of the ocean, tsunami waves do not dramatically increase in height, but as the waves travel inland, they build up to higher and higher heights as the depth of the ocean decreases. So moving back to our question was that which of the following is not a type of storm. And as we just learned that tornado is also a storm, hurricane is a storm, and derecho is also a storm. But tsunami is not actually a storm. Tsunami is just a giant wave. Tsunamis are giant waves which are caused because of either earthquake or ocean bed disturbances. So our answer would be tsunami. Next question, there is a photograph given, and then it is being asked that what is this what is this image showing? Is it a hollow slab, is it a coffer slab, is it a filler slab, or is it a precast slab? So we will just go quickly through all these four terms to be able to answer this question. So hollow core slabs are pre-stressed floor products with either round or shaped voids depending on local requirements. They are one of the most popular, efficient, and long span floor construction components that exist today. So hollow core slabs are usually pre-stressed, and they're very popular right now. And hollow core slabs basically looks like there are holes in the shape of a hexagon or a circular inside them. They're hollow, they have a cavity, that's why they're called hollow slabs. Then coffered slab. Coffered slab is a ribbed structure with reinforced ribs in the lower zone which have mutually perpendicular arrangement. It is also called a waffle slab. Basically there is a grid pattern of beams that are going on, ribs that are going on, that's why it's called a coffered slab. Ribs between the coffers are reinforced, creating concrete beams spanning two ways to support the slab, and it is ideal for longer span slabs and for carrying heavier loads. Then filler slab. Filler slab is alternate slab construction technology where part of concrete in the bottom of slab is replaced by a filler material. It is called a filler slab because in some parts of this slab the concrete is replaced by a filler material. The basic principle of this kind of slab is that the concrete in bottom half of RCC slab is structurally not required as concrete acts as compression material which is required in top half portion of the slab. So this portion concrete is replaced by low cost lightweight filler materials like Mangalore tiles, clay pots, etc. Then precast concrete slab. Precast concrete slab is a construction product produced by casting wet concrete in a reusable mold or form which is then cured in a controlled environment, transported to site and installed in place. So when we go back to this image, you can very clearly see that this is not a coffer slab, this is not a hollow slab, this is not a precast slab, and you can see that the clay pots are being inserted in the slab construction. So we very well clearly know that it's actually a filler slab where the concrete is being replaced by inserting some filler materials there. So our answer is filler slab. Moving to the next question, which of the following forms is supposed to perform the best against heavy wind? Circle, square, rectangle, or hexagon? And as we have discussed it in the first question, how the shape impacts the wind pressure and how different eddies are formed when there are a lot of surfaces involved. So according to this, which of the following is supposed to perform the best against heavy wind? So The surface that would perform best would be the surface which has the lowest pressure. And as we go from this figure, it is evident that a circle would perform quite well. That the circle would perform quite well because it will have the least wind pressure. So our answer would be circle. Now, the following illustration is an example of, so we just discussed all these four terms: the strike slip faults, the normal faults, and the reverse fault. We discussed all these terms and longitudinal fault, and when you come back to this image, you can actually see that this image, in this image, there is first of all a diagonal line of fault, so which means that this is not a strike slip fault. And you can see that in this part is moving up. So what normal fault and reverse fault are opposite of each other. In normal fault, this other part goes up, and in reverse fault, this part goes up. So our answer would be the reverse fault. Question number 15. Which of the following is not a seismic wave? P wave, Q wave, Rayleigh wave, and S wave. So we discussed S wave and Rayleigh wave and love wave. We will just discuss about P waves in this, and I will briefly talk about S wave and Rayleigh wave and love wave also, so that we can answer our question. So P waves, also called primary waves or pressure waves, they travel at the greatest velocity through the earth. When they travel through air, they take the form of sound waves, and because of their speed, they are the first waves to be recorded by a seismograph during an earthquake. They differ from an S wave in that they propagate through a material by alternately compressing and expanding the medium, where particle motion is parallel to the direction of wave propagation. This is rather like a slinky that is partially stretched and laid flat and its coils are compressed at one end and then released. So what happens in P waves is that alternate compression and expansion of particles happen in this kind of wave. While in S wave, what happens is that the wave actually moves up and down. It's like a shaking wave, and the particle motion is actually perpendicular to the direction of wave propagation. And then Rayleigh wave are also called wave rolls, and it rolls along the ground with a complex motion, and it moves the ground up and down and forward and backward. They are also called ground roll, and they travel as ripples similar to those on the surface of water. And people have claimed to have observed Rayleigh waves during an earthquake in open spaces such as parking lots, where the cars move up and down with the waves. And then love wave are surface seismic waves that cause horizontal shifting of the earth during an earthquake, and it was named after Augustus Edward Hugh Love in 1911. So our question is that which of the following is not a seismic wave? So our answer actually is Q wave. However, there is actually a little contradiction here, because as I was searching about all these terms, so I always, because a lot of terms can have different meanings in different contexts, so I always also search what this term means in this context. So I was searching in seismic context what all these waves mean, because these terms are used in a lot of fields and a lot of areas. So actually some of the answers, not all of them, most of them don't even mention it, but some of the answers say that the love waves are also called Q waves, but only two sources say so, that love wave is also sometimes called Q wave. Other sources do not mention that they are called Q waves. So there is a little contradiction in this question, but because most of these sources do not say that that a love wave is a Q wave, then of course the right answer would be Q wave only here. Then levee is found instrumental for protection against fire, flood, earthquake or landslide. We discussed it in the previous question what a levee is. And I would just quickly mention what a levee is. It's a man-made structure that is that runs parallel to the course of a river, and it prevents the flooding of the plains. And the purpose is to keep the course of rivers from changing and to protect against flooding of the area adjoining the river or course. And levees can be naturally occurring structures, and they can be man-made also, and this is how the levee functions and how it looks like. So our answer is flood. Question 17. In most of the airport terminals, space frame with glass cladding is used to maximize daylight usage, ensure long span space, provide the view to external environment. So we will just talk a little about how space frames are utilized and what are their advantages and other points, and then we will answer this question. So open structural forms like trusses, space frames, megastructural openings, and other even areas where structural members are normally connected, they admit light because they are such structures which actually admit a lot of light inside the building. So, what is a space frame? I have mentioned it in previous classes many a times what a space frame is, because a lot of questions were based on this space frame. So, a space frame or space structure is basically a 3D truss. It is rigid, it is lightweight, it is a truss-like structure constructed from interlocking struts in geometric pattern. Usually there is a tetrahedron that is connected in different arrangements to create a space frame. They are used to span large areas with very few interior supports. The space frame structures are used in buildings that span large areas. They are used because of their pleasing architecture. Space frame can be found in airports, stadiums, exhibition halls, swimming pools, and towers. The cost of transportation is less compared to the conventional steel structures. Space structure also allows odd placement of columns, and along with integral cladding and glazing, and modularity can be achieved with this structure. They are very efficient both structurally and functionally. They allow hassle-free erection and geometric balance. They boost the aesthetics of the construction and offer more flexibility. They're easily expandable, and they are built following assembly line approaches with a very minimum amount of seismic resistance. And they provide good daylight, and they provide the views of outside also, because there is always a layer of visibility in these kind of structures. So our question was that in most airport terminals, space frames are used along with glass claddings, and why they are used. What do you think are the main important reason? So I think the most important reason would be ensuring long span spaces without obstructive columns, because in airports it's very important to have those kinds of spaces. Then maximize daylight usage, of course. These structures support a lot of daylight intake, so of course that would also be important. Provide view to the external environment. It might not be the top priority in airport terminals, but because they provide this feature also, so of course this would also be included. So the answer would be D, all of the above. These are few of the examples which show how space frame is being used inside airports. Uh, the last question for today. AAC blocks in building construction refers as autoclaved aerated concrete, added admixture concrete, advanced annular concrete, or added alkaline concrete. So actually AAC blocks are called autoclaved aerated concrete. I would just cover a few facts about AAC, and then of course the answer is AAC blocks, but I would just like to cover a few facts about AAC here. So that in future if needed, because we remember a lot of things with the help of facts. So AAC is made with fine aggregates, cement, and expansion agent that causes the fresh mixture to rise like a bread dough. This type of concrete contains 80% air. That's why it's called aerated, because it has 80% air in it, this kind of block. And because it has 80% air in it, that is why it is very lightweight compared to a brick. So yeah, that's why the term aerated comes in this. So in the factory where it is made, the material is molded and then cut into precisely dimensioned units. The cured blocks or panels of autoclaved aerated concrete are joined with thin bed mortar. Components can be used for walls, floors, roofs, anything. They can be used for anything. The lightweight material offers excellent sound and thermal insulation. Because it is lightweight, it provides thermal insulation too. And like all cement based materials, it is strong and fire resistant. And in order to be durable, AAC requires some type of applied finish, such as a polymer modified stucco, natural and manufactured stone, or siding. The weight of AAC blocks is about 80% less than traditional red bricks and leads to a reduction in the use of cement and steel. The It's about 80% less. The weight is 80% less than a traditional red brick, and it leads to reduction in the cost of cement and steel also, and thus it saves a lot of cost. And it being environmentally environment friendly, they better ensure durability and improve the sound and heat insulation compared to bricks. And our answer is of course autoclaved aerated concrete. So now this is the time for Q&A, and you can ask your doubts and questions. Please type your questions in the chat box. I will try to answer your questions as per my capacity and knowledge. And in case I'm not able to provide you an immediate answer at this moment, I would definitely clarify it in the next session after reading or learning about it. So if anyone has any questions, you can please ask. You can type the questions in the chat box. I would answer your question if you would type it in the chat box. Otherwise, a lot of disturbance is created if we allow people to unmute themselves. Yeah, all the problem solving sessions were recorded and they are uploaded on YouTube. So you must have received emails regarding the access to these YouTube videos, or you can go to the Swayam NPTEL website and you can see there is an option for there is an uh, portal, there is an area for problem solving sessions where you get the link to a Google Drive, which is an Excel sheet, and you have all the video links there, and you also have the drive which has all the PPTs in it. So all the problem solving sessions are available on YouTube, and you can access them. Uh, I read your question that if I can guide what kind of pattern will be there for the exam. So I think the kind of questions that are being done in problem solving sessions and the kind of questions that were given in the assignments, you would get those kinds of questions only. Nothing would be out of the course. Whatever was covered in the NPTEL course, only that part would come. If I may have covered extra points or extra things in my PPT to explain something, those are not part of it. Whatever was covered in the NPTEL course, in the videos that you would have seen for this course that Professor Shubhajit Sadhu Khan has made, only that content will come. There are no specific notes available. You can have these PPTs that I have made on these questions, and you have the PPTs that Shubhajit Sadhu Khan sir has made. They're available on the Swayam website. You can access all those presentations, and also I think you can also access the transcript notes, and the videos are always available. So there is nothing as such as notes, but all the content is available. The videos are available to you, the transcripts of the videos are available to you, all these PPTs would be available to you. All the problems solving sessions recordings are available to you. All these points are available to you. Oh, I was not aware of this, that there are systematic chapter notes that are being given in other courses. As the TA for this course, my duty was to conduct the live sessions, and I was not asked to create any notes, or I don't know if the professor in charge, the course instructor, created any notes extra or what. But my as the work that was assigned to me as a course TA was to take these live sessions where I solved the previous year questions. I am not at the liberty to give that mobile number, and I also do not have it. But I think you can email him if you wish to. You can easily find his email contact online, or maybe on the NPTEL website you might have it. Welcome. So we would stay in the call for 10-15 minutes. If anyone has any questions, you can ask. If you don't have any questions, you can leave the meeting. Yeah, thank you so much. I hope you guys liked the session. And I'm so sorry that this has happened, that the last session would happen after the exam. So, since no one is present in the meeting, and we have waited for 15 minutes to see if one is going to join, we are concluding to this session, and we will have the last session next week on Tuesday, and I'll see you there. We would be doing week 8 at that time. Thank you.